In this section, we're going to talk about finding infinite geometric sums or infinite geometric series. The words series and sums are oftentimes interchangeable. So right here is a sum or a series of a lot of positive terms, and if you watched the last video about geometric sequences, what I want you to notice is that this is a geometric sequence where the terms are being added up. So important to note is if you take one term, 7/2, and divide it by the term that comes before it. So divided by 7. So let's see, that'd be 7/2. 7/1 becomes times 1/7, and we get 1/2. Okay, and then if we take two other consecutive terms, say 7/16 divided by 7/8, which would be 7/16 times 8/7, and reduce, again, we're going to get 1/2. In fact, if we take any two terms in this series and divide the one after by the one before, we're going to continue to get the same number, 1/2. And if you saw that previous video, that 1/2, that common ratio, is what we call R. So R is our common ratio. So indeed, this is a geometric sequence where the terms are being added up. In other words, it's a geometric series or a geometric sum. This one is important too because of the ... at the end and nothing following it. So this series goes on forever. The next term would be 7/64 and 7/128, and it never, ever, ever ends. What's ironic about this, though, or interesting about it, is that though we're adding up an infinite number of positive terms, we're not going to get an infinite answer. We actually get a finite answer for this particular sum. If you would question that, if that doesn't make logical sense to you, I really recommend that you watch the video that I posted previously about visual explanation of geometric sums. It's a really cool video. Okay, back to this problem. So, going back to this problem, when we're adding these terms up, we're going to have a formula kind of similar in the way that we had one for arithmetic sequences. And our formula is going to look like this. If we had, in general, say a geometric sum, A1 is our first term, our next term would be A1R squared, A1, R cubed. Remember, we get each next term by continually multiplying by another form of our common ratio or common form of R, and that goes on forever. The sum that we get is equivalent to A1, which would be the first term, divided by 1 minus R, or common ratio. Okay, one other thing I want to point out is there is a way to write this in summation notation, and it's important to get used to that. So here's how we would write this with a sigma. One way to write this with a sigma, remember, means sum or add, and we're adding up all of our terms, A1 R to the n minus 1. So if you remember in the geometric sequence video, we came up with that generalized formula for the terms of a geometric sequence. And n starts at 1, and in this case, it doesn't stop. It goes to infinity. So these are two different ways of writing the same thing. And the formula is just the first term over 1 minus the common ratio. Cool. So going to this example up here, the sum would be the first term in this problem is 7. So that is what we would put in our numerator. 7 over, there we go, 1 minus the common ratio, which we already found out was 1/2. Okay, so your first term, 7, or A1, divided by 1 minus the common ratio, 1 minus whatever your R is. Doing a little arithmetic here, 1 minus 1/2 is 1/2. So we have 7 divided by 1/2, which is the same as 7 times 2 over 1, which is 14. So if we add up all the terms, 7, 7 over 2, 7 over 4, plus 7 over 8, and so on, apparently we get the sum 14. So this formula that we're using here for the sum of a geometric sequence, the terms of a geometric sequence, this A1 over 1 minus R, is a really important formula. There is one condition. This doesn't always work. And that condition is your R has to be less than 1. Well, actually, R can be between -1 and +1. So that is the same thing as just saying the absolute value of R has to be less than 1. So if your R, let's say your R wasn't 1/2, if your R was 3/2, which is bigger than 1, then if R is bigger than 1, or the absolute value of R is bigger than 1, then the series diverges. So diverging means that it adds up to an infinite number. Converging means that it adds up to a finite number, and we can find the number using this formula. Okay, let's do another example. All right, let's find the following sum: 3 plus 6 plus 12 plus 24 plus 48, and so on. And what I want you to notice about this is these numbers here are getting really big. In the previous example, the numbers were getting smaller. 7/2 is smaller than 7/4, which is smaller than 7/16, and 7/8. These numbers are getting bigger and bigger and bigger, which is really different. So first of all, let's just make sure that this is a geometric sum indeed. So let's see, we'll take 2 terms, divide the latter by the former. So 6 divided by 3 is 2. So hopefully that's our common ratio. Let's take another 2 terms. Let's take 24 and 12. 24 divided by 12 is 2. Yep, sure enough, it's a geometric series, and R is equal to 2. So instead of popping into our formula, A1 over 1 minus R, we can't use that formula for this one because that formula only works for R being less than 1, or the absolute value of R being less than 1. Since in this case, R is too big, since R is 2, which is bigger than 1, then this series diverges. And there's nothing more to do. Sometimes people would say the series adds up to infinity, but most textbooks would just say the series diverges. Okay, that wasn't very interesting. Let's do a different problem. Okay, let's find this sum. 1/4 plus 1/16 plus 1 over 64 plus 1 over 256, and so on to infinity. So first of all, got to verify it's geometric. So take the latter term and divide it by the former one. So that would be 1/16 multiplied by 4 over 1, which reduces to 1/4. Oh, interesting. Okay. Let's take any other 2 terms. So 1 over 256 divided by 1 over 64. 256 times 64 over 1, and using your calculator, go right ahead. This reduces to, again, 1 over 4. So making sure all of these are equal to the same. This is certainly a geometric series. Every term is multiplied by the same number r of 1/4 and being added up. Also important is that 1/4 is smaller than 1. So the series converges. Okay, and if it converges, it's going to converge to the formula a1 over 1 minus r. Well, this is kind of an odd problem. Our r is 1/4, and our a1, which is our first term, is also 1/4. That happens, though, from time to time. So first term is 1/4, or happens to be the same number, also be 1/4. So again, a little bit of arithmetic here. 1 minus 1/4 is 3/4. So 1/4 divided by 3/4 is the same thing as 1/4 times 4/3. And when we reduce that, we get 1/3. Now, actually, I picked this sum for a reason. If you look at the previous video, that picture right there of those nested triangles is a cool representation of the sum 1/4 plus 1/16 plus 1/64 to infinity that adds up to 1/3. It's a cool graphical representation of that issue. Okay, let's do a couple more examples. A lot of these problems are not written out in term-by-term format. They're written in sigma notation. So it might be helpful if you get a problem like this to see how it's related to the previous ones by writing this out in term-by-term notation. So what that would mean is, let's say n equals 1, because that's what it says that we should start with. Start with n equals 1 for our first term. And plugging in n equals 1, we have 4 times negative 2/3 to the 1 minus 1. Well, 1 minus 1 is 0, and anything to the 0 power is 1. So this is 4 times negative 2/3 to the 0, which would be 4 times 1, or 4. Let's see, the next term would be when n equals 2. 4 times negative 2/3 to the 2 minus 1. Let's see, 2 minus 1 is 1, so this is 4 times negative 2/3, which would be a negative 8/3. Okay, let's just do one or two more. Let's see, n equals 3, 4 times negative 2/3 to the 3 minus 1 is 4 times negative 2/3 squared. Well, 2/3 squared is, what, 4 over 9? So 4 times 4 over 9 is 16 over 9, and it's positive because it was squared. And we can do one last one. When n equals 4, we have 4 times negative 2/3 to the 4 minus 1. 4 minus 1 is 3. So 4 times negative 2/3 cubed. Let's see, giving myself a little bit of room. That would be 4 times negative 8 over 27, which is negative 32 over 27. And so on. Okay, a little strange that we have alternating terms here, positive, negative, positive, negative. But if you remember in the previous section for geometric sequences, we can have r be a negative number, continually multiplying by negative, and that would change the sign of each term. So let's double check and see if this is in fact geometric. So negative 8/3 divided by 4 is negative 8/3 times 1 over 4. And the 8 and the 4 reduce to negative 2/3. Okay. Taking two more terms, negative 32 over 27 divided by 16 over 9 gives negative 32 over 27 times 9 over 16. And reducing that, again, we get negative 2/3. So this is, in fact, a geometric series, which means that we could look at the r to decide if it converges or diverges. Now remember, its absolute value had to be less than 1, so the absolute value of negative 2/3 is positive 2/3, and that is certainly less than 1. So this series converges. And since it converges, we know it converges to a1 over 1 minus r. Okay, so a1 is our first term. That first term was 4. The first term is 4. 4 over 1 minus r. We found out r is negative 2/3. So negative 2/3. Okay, doing some arithmetic here. 1 minus negative 2/3 is, let's see, plus 2/3. So that would be 5/3. 4 divided by 5/3 is 4 times 3/5, which would be 12 over 5. Cool. Something I want you to notice about this problem is everything that we did here, we could have skipped. Notice in this problem, I'll highlight these, your 4 was your first term. It is not a coincidence that 4 was this coefficient out here in front of our exponential. Also, negative 2/3, if I erase back a little bit, change this back to minus a negative 2/3. That negative 2/3 was our r, which we found here, but it's not a coincidence again that negative 2/3 is the base of our exponent. So instead of doing all the work on the right-hand side, we could have very quickly jumped to a1 is 4 and r is negative 2/3. That would have saved us a bit of time. So when we do our last example, let's do that. All right, last example. So for this last example, let's use sigma notation one more time and find the sum k goes 1 to infinity of 1/2 times negative 1/3 all to the k minus 1. One thing I'd like you guys to notice is that I'm using k's instead of n's for this. What we call this the index. It's just the counter, the first one, the second one, the third one, the fourth one, up until whenever it tells you to stop. And it really doesn't matter what variable they use for this, as long as this k matches this letter up here. Okay, so let's save ourselves some time. In the previous one, we learned that a1 is that first coefficient, or is the base of the exponent. So in this case, if r is negative 1/3, the absolute value of negative 1/3 is positive 1/3, definitely less than 1, so it converges. And since it converges, we can use the formula a1 over 1 minus r, which would be 1/2 over 1 minus negative 1/3. Okay, minus a negative 1/3 is positive 1/3, so that's 4/3. 1/2 divided by 4/3 is 1/2 times 3/4, 3/8. Cool. So let's really quickly summarize what we have. Okay, going back to the series that we had on the very, very first page of this, a1 plus a1 times r plus a1 times r squared plus a1 times r cubed and so on. This infinite geometric series diverges if the absolute value of r is too big, is bigger than 1. If the absolute value of r is less than 1, it converges, and it converges to a1 over 1 minus r. And one last remark to make is this can be also written in series form. I'm going to pick n this time as my index counter. N goes from 1 to infinity of a1 times r to the n minus 1.